On August 4, 2026, NASA carried out an extraordinary engineering operation involving one of humanity's oldest active spacecraft. It was not a launch, not a repair mission, and certainly not a cosmic explosion. It was a carefully planned attempt to keep Voyager 2 alive. The spacecraft is now more than 21 billion kilometers from Earth, traveling through interstellar space. A radio signal needs roughly 20 hours to reach it, and another 20 hours are required for its response to return. That means every command is effectively a long-distance gamble. Engineers cannot simply make a change and immediately see whether it worked. Voyager 2 was launched in 1977. Its onboard computer has an almost unbelievably small amount of memory compared with modern electronics, yet this aging machine continues to return scientific information from a region of space no other operating spacecraft has reached. Its power source is also slowly fading. Voyager does not have solar panels supplying it with electricity. Instead, its radioisotope thermoelectric generators produce power from the natural decay of plutonium. As the radioactive material decays, the available electrical power gradually falls. The spacecraft loses only a few watts of usable power each year. On Earth, that sounds insignificant. In interstellar space, those few watts can determine whether an instrument continues collecting data or disappears forever. That is why NASA engineers have been forced to make increasingly difficult choices. Over the past several years, instruments and systems have had to be switched off to conserve electricity. Every shutdown represents a trade. Sacrifice something today so that something else can survive tomorrow. Without another intervention, Voyager 2 would have been forced to give up another important function before the end of 2026. Instead, engineers designed a complicated power-saving procedure. The operation involved shutting down higher power equipment while activating lower power alternatives, all while keeping the spacecraft within its extremely narrow operating temperature range. The commands had to travel across billions of kilometers before anyone on Earth could know whether the plan had succeeded. There was no technician standing beside Voyager with a toolbox. There was no emergency override. If a component became too cold or a critical system failed, there would be no repair mission coming from Earth. The spacecraft had to survive on its own. Engineers spent months testing the procedure and studying how Voyager might respond. Eventually, the commands were transmitted into the darkness. Then came the waiting. For almost 2 days, the team had to wait for confirmation. And eventually, the signal arrived. The maneuver had worked. By rearranging how Voyager 2 uses its remaining power, engineers were able to preserve the operation of its remaining scientific instruments for longer than would otherwise have been possible. That achievement matters because Voyager 2 is not simply an old spacecraft still transmitting a signal. It is one of humanity's only direct scientific windows into interstellar space. To understand why that matters, we need to look at where Voyager is. Our solar system is surrounded by a gigantic region called the Heliosphere. It is created by the continuous stream of charged particles flowing outward from the Sun. This solar wind extends far beyond the planets and forms a kind of enormous protective bubble around our solar system. Eventually, that outward-flowing solar wind encounters the material filling the space between stars. The boundary between these environments is called the Heliopause. For decades, scientists could study it only through models and indirect observations. Then Voyager changed everything. Voyager 1 crossed the Heliopause in 2012. Voyager 2 followed in 2018, traveling through a different part of the boundary. That second crossing was extremely important because scientists suddenly had another measurement from another location. 2 spacecraft. 2 trajectories. 2 glimpses of the same enormous boundary. And what they discovered was far more complicated than the simple wall scientists once imagined. As Voyager crossed the Heliopause, the spacecraft detected a dramatic decrease in solar particles and an increase in high-energy particles originating beyond the heliosphere. That confirmed that the spacecraft had entered the interstellar environment. But the measurements also revealed unexpected conditions. Near the boundary, Voyager detected plasma temperatures far higher than many earlier expectations. The numbers sound almost impossible. Tens of thousands of Kelvin. At first glance, that seems like an environment hot enough to destroy anything that enters it. But temperature in an extremely thin plasma does not behave the same way it does in Earth's atmosphere. There are so few particles that enormous particle energies do not translate into the kind of heat transfer we experience on Earth. So Voyager did not melt. Instead, it continued traveling through the strange region and sending information back. And that information raised an even bigger question. Why is the plasma near the heliosphere's boundary so energetic? What processes are creating those conditions? And what does that tell us about the way our solar system interacts with the space between stars? The surprises did not end there. Voyager's measurements also revealed unexpected behavior in the magnetic environment around the Heliopause. Scientists had expected the magnetic field associated with interstellar space to behave differently from the magnetic field generated by the Sun. Instead, observations showed an unexpectedly similar orientation across the boundary. That does not mean the two environments are identical. It means the boundary is more complicated than a simple dividing line between two completely separate magnetic systems. The Heliopause appears to be an active, dynamic region where solar and interstellar influences interact. Voyager also observed evidence that plasma becomes compressed around the boundary. That suggests the edge of the heliosphere is not a perfectly smooth shell. It is a complicated physical environment with changing density, magnetic fields, particles, and energy. And perhaps most importantly, some particles from inside the heliosphere can cross into the surrounding interstellar environment. The boundary is not an absolutely sealed wall. It behaves more like a dynamic interface. That matters because the heliosphere plays an important role in shielding the solar system from some forms of galactic radiation. Understanding how particles move through its boundary can help scientists understand how our solar system interacts with the larger galaxy. And Voyager 2 has a special advantage. Voyager 1's plasma instrument stopped functioning decades ago, meaning scientists have had to rely heavily on other measurements to understand the plasma surrounding that spacecraft. Voyager 2 still has an operational plasma experiment capable of directly measuring important properties of the surrounding environment. That makes Voyager 2 exceptionally valuable. It is not simply confirming what Voyager 1 discovered. It is giving scientists another perspective. Another location. Another set of measurements. And another opportunity to determine which features of the Heliopause are universal and which depend on where the spacecraft happens to cross it. That is why extending Voyager 2's scientific lifetime is so important. Every additional month produces observations from a location humanity cannot currently reproduce. There is no replacement spacecraft sitting nearby. There is no second probe waiting behind Voyager 2. And there is no quick mission that could be launched today and arrive in interstellar space next year. An interstellar probe has been discussed for years, but any future mission would require enormous planning and would take decades to reach a comparable distance. Voyager is already there. It has been there for years. And it is still working. Think about what that means. A machine launched in the 1970s is operating billions of kilometers away, with technology designed nearly half a century ago, while engineers on Earth carefully manage every remaining watt of power. Its transmitter operates at a remarkably low power compared with modern communication systems. Yet that tiny signal travels across an enormous emptiness and is detected by the giant antennas of NASA's Deep Space Network. By the time Voyager's signal reaches Earth, it is incredibly weak. But inside that faint radio transmission can be measurements of magnetic fields, plasma, cosmic rays, and energetic particles from the space between stars. Information gathered from a location no human has ever physically visited. And eventually, the power will run out. The exact end of communication depends on how long the spacecraft can continue producing enough electricity and maintaining its systems. The probes may remain in communication for years after their remaining science operations decline, but there will eventually come a moment when Earth receives the final usable signal. After that, Voyager will continue moving. It will not stop. It will not fall out of the sky. It will simply become silent. The spacecraft will continue its journey through the galaxy long after the antennas on Earth can no longer hear it. And what we lose at that moment will not simply be an old machine. We will lose a direct scientific connection to the environment surrounding our solar system. We will lose the ability to measure that particular region of interstellar space from inside it. We will lose another piece of a mission that has already lasted far beyond its original expectations. But perhaps the most important lesson from Voyager is not that the spacecraft is old. It is that the universe repeatedly becomes stranger when we finally measure it directly. Scientists built models of the heliosphere from everything they knew. Then Voyager crossed the boundary. The measurements revealed unexpected temperatures, complex magnetic behavior, changing particle densities, and a boundary that behaves less like a solid wall and more like a constantly shifting interface. The spacecraft did not prove that physics was wrong. It showed that our understanding was incomplete. That distinction matters.